Okay. Thank you very much for the invitation. It's a big pleasure to speak here. So today I'm going to talk about barcode entropy and relative symplectic cohomology. So here is some motivation. So Sinelli, Ginsburg, and Gurel introduced the barcode entropy, which can capture the complexity of a Hamiltonian diffeomorphism. More precisely, the barcode entropy, which I denote by h bar of phi h of the Hamiltonian diffeomorphism, admits an upper bound in terms of the topological entropy of the Hamiltonian diffeomorphism. And moreover, they established a non-trivial lower bound of this barcode entropy. And the lower bound is also given by the topological entropy, and the lower bound is the topological entropy of the Hamiltonian diffeomorphism, restricted to a compact hyperbolic invariant set of the Hamiltonian flow. So as a consequence, when the ambient symplectic manifold is a surface, uh, the following equality holds, which is the Barcode entropy is equal to the topological entropy of the Hamiltonian diffeomorphism. And here are some related results. Since the definition of the Barcode entropy is quite general, so it can be adapted to numerous Floer-theoretic settings. A more theoretic notion of Barcode entropy was introduced by Ginsburg, Gurel, and Mazzucchelli, and it was shown to be comparable to the topological entropy of the geodesic flow. And this framework was extended to the symplectic cohomology of a Liouville domain by Fender, Lee, and Son. And the Barcode entropy there was shown to admit an upper bound in terms of the topological entropy of the Reeb flow on the boundary of the Liouville domain. And this result was later complemented by Sinelli, Ginsburg, Gurel, and Mazzucchelli by providing a lower bound for the Barcode entropy of the symplectic cohomology of a Liouville domain. And recently, analogous upper and lower bounds for the Barcode entropy have been obtained in the setting of wrapped Floer cohomology by Fernandez. And here is the main result of today's talk. So our main result concerns the Barcode entropy in the setting of relative symplectic cohomology introduced by Vergunis. So here is the main result. Let M omega be a closed symplectic manifold and K be a Liouville domain sitting inside of M, and assume that M omega is symplectically spherical, and the boundary of K with the canonical contact form is index bounded, which I will explain later. Then there exists a constant C, which depends on the pair M and K, such that the Barcode entropy of the relative symplectic cohomology is less than or equal to the constant C times the topological entropy of the reflow of the boundary of the Liouville domain K. So one immediate consequence is that since the topological entropy of the smooth map is always finite, our Barcode entropy is also finite. That's one immediate consequence. And here is a remark on the constancy, how it is constructed. So we fix a color neighborhood of the boundary of K, which can be symplectically embedded inside M. And we are going to consider Hamiltonian functions that are linear with respect to the radial coordinate on a subregion of the color. And the constant C actually comes from the infimum of the slopes of suitably chosen Hamiltonian functions. And the optimal bound is obtained by varying the color length up to its maximal value allowed by the embedding of K inside M. So in that sense, this constant C reflects the relativeness of K inside M. I will explain later. And some preliminaries. Let me start with the persistence module. So a persistence module is a pair V pi where V is a collection of finite dimensional vector spaces, and pi is also a collection of maps from V tau 1 to V tau 2 whenever tau 1 is less than or equal to tau 2, and it satisfies the following conditions. For any real number tau, the structure map pi tau tau is just the identity map on V tau. And for any increasing number tau 1, tau 2, tau 3, this composition rule holds. And there exists a closed, bounded from below and nowhere dense subset, which I will call spectrum, such that the structure map of V tau 1 to V tau 2 is an isomorphism whenever tau 1 and tau 2 are in the same connected component of R, the set of real numbers minus the spectrum. And for any real number tau and any tau prime, which is less than or equal to tau and sufficiently close to tau, the structure map V tau prime to V tau is an isomorphism. And last, there exists a number tau 0, such that V tau, the vector space is always 0 for tau less than or equal to tau 0. And usually we'll use the notation V to denote the persistence module. So when everything is clear. And here is a crucial example of this persistence module. So for a fixed interval I, the interval persistence module, we can define the interval persistence module. And the vector space is defined by the base field F whenever the number tau is in the given interval, and it is 0 when tau is outside of the interval. And the structure map is the identity map whenever two numbers are in the interval and 0 otherwise. Then why is this example so important? Because of this normal form theorem. Roughly speaking, every persistence module can be decomposed as the direct sum of those interval modules. So precisely, let V pi be a persistence module, then there exists a countable collection of interval and multiplicity, such that the given persistence module is isomorphic to the direct sum of the interval modules with its multiplicity. And moreover, this decomposition is unique up to permutation. So to any persistence module, there exists a unique multiset consisting of intervals and its multiplicity. And we call this multiset the barcode of the persistence module, and an element of barcode is called a bar of persistence module. And some notations. So for a barcode and a positive number epsilon, let B epsilon V be the set of bars in the barcode of length greater than epsilon. And lowercase b epsilon v is just the number of elements of this uppercase B epsilon v. And truncation of the persistent module. So the truncation of V as sigma is defined as follows. So the vector space at tau is just V tau from the given persistent module whenever tau is less than the truncation point and 0 otherwise. And the structure map is defined in an analogous way. So we still use the same structure map whenever the bigger number tau 2 is less than the truncation number, and the structure map is 0 otherwise. So it's really a truncation. Okay, then this is the definition of the barcode entropy introduced by Sinelli, Ginsberg, and Gurel. So let V be a persistence module and epsilon be a positive number. Then the epsilon barcode entropy of this persistence module V is defined so we start from the persistence module V, and we truncate it at sigma, some number. And we count the number of bars of this truncated persistence module of length greater than epsilon. And the epsilon barcode entropy is defined by the exponential growth rate of that number. And the barcode entropy is just taking epsilon to 0. Okay, next we are in the realm of dynamical systems. I will briefly explain what topological entropy is. So let X, D be a compact metric space and F map from X to X be a continuous map. And we can define an increasing sequence of metric using this original metric and this function F as follows. Here, F to the I denotes the composition of F with itself I times. And let BFX epsilon L is just an open ball of radius epsilon centered at X. And a subset E of X is said to be L epsilon spanning if the whole space X can be covered by the epsilon balls using this metric centered at the point in X. And here's the definition of the topological entropy due to Bowen. So let XD be a compact metric space and F be a continuous map, and SDF epsilon L be the minimal cardinality of an L epsilon spanning set. This always exists because X is assumed to be compact. And then the topological entropy is defined by the exponential growth rate of this number. That's the definition of the topological entropy. But in fact, we are not going to use this definition directly. Instead, we're going to use a different type of entropy, which is the following. Let X be a smooth Riemannian manifold and F be a smooth map from X to itself. And we denote the graph of F by gamma F, which is the set of X comma F of X in the Cartesian product X times X. And for a smooth manifold Y of X, the exponential volume growth rate, I will call this volume entropy. So volume entropy of F restricted to Y is defined to be the exponential growth rate of the volume of the graph of the iteration of L restricted to Y. So that's the definition of the volume entropy. So now we have two types of entropy. One is topological, and the other one is volume. And those are related by the following theorem by Yomdin. Let X be a smooth Riemannian manifold and F be a smooth map. Here, smooth means C infinity smooth. Otherwise, we need some additional term. So, and for C infinity smooth submanifold Y of X, we have, so volume entropy is always less than or equal to the topological entropy of a map F. That's Yomdin's theorem, which is one of our main ingredients to prove the main result. Okay, now we are going to say something about symplectic geometry. So the Novikov field is defined by the set of formal power series where T is a formal variable and coefficients are rational and the exponents are real and the limit of exponent is infinity. And there is a valuation map from this Novikov field to the union of the set of real number and the infinity. And valuation of the non-zero element of the Novikov field is given by the minimal exponent where its coefficients are non-zero. And the valuation of the zero element is defined to be the infinity. Sorry. And for any real number R, we define lambda greater than or equal to R. And this is just a pre-image of the infinite interval R to infinity under the valuation map. And in particular, lambda greater than or equal to 0 is called the Novikov ring. One more. Let's say A is a module over the Novikov ring, and we have two numbers, R prime and R prime is greater than R. And then there exists a map from the Novikov ring modeled out by lambda greater than or equal to R prime to Novikov ring truncated by lambda greater than or equal to R. And this map still induces after tensoring with A. And this forms an inverse system using those as morphisms. And since we have like inverse system, you can consider its inverse limit. And the inverse limit of this is called a completion of A, which is the main ingredient to define the relative symplectic cohomology. Okay, now we can define the relative symplectic cohomology. So let M omega be a closed symplectic manifold and K be a compact subset of M. And we choose a sequence of Hamiltonian functions such that HI restricted to S1 cross K is negative, and this sequence is increasing, and the limit of HITX is 0 when X lies in K, and the limit is infinity when X lies outside of K. So that's the cofinite sequence that we are going to use to define the relative symplectic cohomology. So using those sequence, we can form a one ray of Floer complexes where all the arrows are continuation maps. And note that here Floer differential and continuation maps are weighted by the topological energy of the Floer cylinder. And the topological energy is defined by topological energy of U is defined by the integration of H over Y and minus the integration of H over X and plus the symplectic area of the Floer cylinder. Okay. So to define the relative symplectic cohomology, so we start from the sequence that we just described and consider their Floer complexes. And those Floer complexes form a direct system. So we can take its direct limit. And last but not least, we need to complete the whole complex. And this completed complex is still a chain complex, and we take the cohomology. And that's the definition of the relative symplectic cohomology. And this can be reformulated when K has a contact type boundary. Let K be a compact domain with contact type boundary, which means K is a submanifold of M of codimension 0 with smooth boundary, and there exists a vector field X called the Liouville vector field on a neighborhood of boundary K, such that the Lie derivative of omega with respect to X is omega itself. And one nice feature of this contact type boundary is that it admits a contact structure, and the contact form alpha is given by the interior multiplication of omega with respect to this Liouville vector field, and we restrict it to the boundary of K. So we will denote the Reeb vector field and Reeb flow on the boundary of K by R alpha and phi alpha T respectively. And we can consider its symplectic completion, K hat, which can be obtained by attaching K with boundary K times the half-infinite cylinder, 1 to infinity, along the flow of the Liouville vector field. But since M is assumed to be compact, closed, the symplectic completion K hat cannot be embedded inside of M. But we can still consider a small color neighborhood, boundary of K times the interval 1 to 1 plus 3R1 for some R1. So we're going to use that. Okay, we say that a Hamiltonian function H is contact type K semi-admissible if it satisfies the following. So in the original definition, H was assumed to be negative on S1 cross K, but we just assume that H is zero on S1 times K. And on the color, it's given by a function uh, depending on the radial coordinate. And we are going to divide the color into three pieces. So on the first piece, this function is a strictly convex increasing function. And on the second third of the color, it is given by a linear function. And I will denote the slope of the linear function by SH and the y-intercept by negative IH. And here the slope SH is not a period of any Reeb orbit of the boundary of K. And on the last third, it is given by a strictly concave and increasing function. And outside of the union of K and the color, it's just a constant function. And I will denote that constant by CH. So here is the reformulation. Basically, it says that the relative symplectic cohomology can be defined as a limit and completed limit of the increasing multiple of a single Hamiltonian, semi-admissible Hamiltonian function. Here is our setting. A symplectic manifold M omega is said to be symplectically spherical if the symplectic form is zero on the spherical classes, and the first Chern class also vanishes on spherical classes. And our subset K is required to be a Liouville domain, which means that the Liouville vector field is defined over K. And the contact manifold boundary K is index bounded if for each integer K, the set of periods of Reeb orbits on the boundary, which are contractible in M, have Conn-Alexander index K is bounded. So under this setting, we can go further. So for K semi-admissible Hamiltonian function, Hamiltonian vector field is given by a negative H prime R times the Reeb vector field on the color. So every T periodic Reeb orbit gamma on the boundary corresponds to one periodic Hamiltonian orbit X, gamma R star, with the derivative of H at R star is the period of the Reeb orbit gamma. And this is the convention that I am following for the action functional. And it can be easily seen that this action functional can be computed in terms of R and H because XH is given by this. And one more thing to note is that Floer trajectory increases the action. So actions are increasing along the Floer trajectory in my convention. And the action filtration of the relative symplectic cohomology is defined in a natural way. So we start from K semi-admissible function and consider its filtered Floer complex and take their direct limit and then complete the complex and take its cohomology. That's the definition. And again, as before, this can be written in terms of a single K semi-admissible Hamiltonian as follows, which is analogous to the thing that we saw already. Some estimates. So for semi-admissible Hamiltonian functions, there are four types of Hamiltonian orbits. So first one is critical point contained in K. And second one is the non-constant Hamiltonian orbit coming from H1, the convex part. And the third one is the non-constant Hamiltonian orbit coming from H2, the upper concave part, and critical point lying outside of K from the constant part of the function. So we refer to the first two types of orbit as lower orbit and to the latter two types of orbit as upper orbit. And then we can compute their actions, lower and upper orbit. So first, let X be a non-constant lower orbit. So R star lies in the interval 1 to 1 plus R1. Then its action, so the first line is just the definition. And since H1 is 0, this HR star can be written as this integral. And since H is convex, H prime R is always less than or equal to H prime R star. And since H prime R star is just a constant, we can compute easily. So we have minus H prime R star at the end. And since H is increasing, H prime R star is positive, so the action is negative. So any lower orbit have negative action. Then how about the upper orbit? So let's say X gamma R star is a upper orbit. Then definition, and I just add and subtract CH, which is the constant part of outside of K and the color. And the two terms in the middle can be written as the minus of this integral because H1 plus 3R1 is the constant CH. And since H is concave, this quantity is greater than this quantity. I just replace H prime R by H prime R star because of the concavity. And after all the calculation, we arrive at this point. So the constant CH minus 1 plus 3R1 times H prime R star, which was the period of the corresponding Reeb orbit. And I will denote that orbit, the period by A gamma. So so if you fix Collins-Gender indices, then this action can be made positive because we are assuming that boundary of K is index bounded, which means after fixing Collins-Gender index, A gamma is bounded. So if we choose H sufficiently large, upper orbits can be made positive due to the index boundedness of the boundary of K. Okay. So let H be a K semi-admissible Hamiltonian function, and for each integer K, let CFKU of sigma H be the set of upper orbit of sigma H. For a sufficiently large sigma, we can make upper orbits of Collins-Gender index K minus 1, K, and K plus 1. They all have the positive action. And we can consider this chain complex, which consists of upper orbits of sigma H of degree K minus 1, K, and K plus 1. This is actually indeed a chain complex because, as I said earlier, actions are increasing along the flow trajectory. And analogously, we can define this chain complex consisting of lower orbit of degree K minus 1 and K plus 1. And now using this, we have the following proposition, which has the filtered relative symplectic cohomology is generated by lower orbit. So we don't actually need the upper orbit in our setting. And what's noticeable is that we don't even need a completion part here. We just take limit of lower orbit and then take homology. And actually, we can go further. Okay. So we define a function, uppercase A sub h, by we're just following the definition of the action functional that was explained earlier. So in the convex part, uppercase AH is given by like minus R times H1 prime R plus H1 R, and concave part is defined analogously. Then for any non-constant orbit, X, gamma R star, the action of X is just uppercase A H R star. One more step. We introduced another variant of the action functional, which expresses the action in terms of the period of the Reeb orbit. And this can be done by composing the uppercase AH by the inverse of the H prime. So I will denote this function by lowercase AH. And the first one, in the convex part, it's just composition of the uppercase AH with the inverse of the H1 prime, and the concave part analogously. And in particular, the first one, we have some estimate for the derivative of the first one, which is the derivative lies between -1 minus R1 and -1. And from this inequality, we get this chain of inequalities, which will be useful later when we compare the number of bars of two persistence modules. Okay, here is our main ingredient. So here, before we saw that the relative symplectic cohomology is defined, we don't even need to complete the complex. But if you can control the action window properly, we don't even need to take the limit. So precisely let A be a finite subset of the set of integers, and H be a contact type K semi-admissible Hamiltonian function. Then for any sufficiently large sigma, the filtered relative symplectic cohomology is isomorphic to the Floer cohomology of a single Hamiltonian sigma H, with the action window from lowercase a sigma H tau from to 0. Here, the tau moves from 0 to the slope of sigma h, and the slope of sigma h is equal to sigma times the slope of h. Then how to choose this sigma? Since the constant part of sigma h is sigma times ch, so we can choose sigma sufficiently large so that all relevant upper orbits H have positive action. And because, again, this is possible because of the index boundedness assumption of the boundary of K. And the rest of the proof is quite involved, so I will omit it. Okay, some Floer-theoretic Barcode entropy. So for each K, this assignment defines a persistence module, and the structure maps are induced by inclusion maps. And the full relative symplectic cohomology is the direct sum of each degree. So the barcode of the relative symplectic cohomology is just the union of barcode from each degree. And this is the definition of the relative symplectic cohomology, Barcode entropy. So we start from this persistent module, relative symplectic cohomology. We truncate it as sigma, and we count the number of bars of length epsilon, length greater than epsilon, and consider it exponential growth rate. and the Barcode entropy is just taking epsilon to 0. One more. We can also define the Barcode entropy associated with a Hamiltonian function because this assignment also defines a persistence module. And the Hamiltonian Barcode entropy of this Hamiltonian function h is defined analogously from the definition. So we count the number of bars of a Floer cohomology of sigma h of length greater than epsilon and consider its exponential growth rate and take epsilon to 0. Oh, one more. So in view of previous discussion, which says filter the relative symplectic cohomology is isomorphic to the Floer cohomology of a single Hamiltonian function with the proper control of action window. So we consider the persistence module tau to the Floer cohomology of H, and the action window is minus tau to 0. And I will denote this by HF negative because it has only negative actions. So the negative Hamiltonian Barcode entropy is defined in an analogous way. I think I explained a lot of times. So we now have several types of Floer-theoretic barcodes, and some of them are comparable. So there exists a contact type K semi-admissible Hamiltonian function H, such that for any positive number epsilon, the epsilon relative symplectic Barcode entropy is less than or equal to the epsilon negative Hamiltonian Barcode entropy. And hence, taking epsilon to 0, we have two Barcode entropy are comparable. The Hamiltonian one is bigger. Okay, now I will briefly explain the proof of our main result. Some more ingredient. Let M prime omega prime be a symplectic manifold and L be a Lagrangian submanifold of M prime. For a compact manifold B, possibly with boundary, a smooth map psi from B times L to M prime is called a Lagrangian tomograph of L if it satisfies the following. First, this map psi is a submargin, and the map psi sub S, which is given by fixing an element S in B, and this map psi S is an embedding for each S in B, and the image of L under this map psi S is a Lagrangian submanifold of M prime omega prime for each S in B, and the image LS is Hamiltonian isotopic to each other. Then we call this map a Lagrangian tomograph, and the existence of this Lagrangian tomograph was proved in the paper by Sinelli, Ginsburg, and Gurel. And they did more. So we can have like Crofton's inequality. Setting is the same. Let M prime omega prime be a symplectic manifold, and we have L1, L2, two Lagrangian submanifold of M prime, and psi is a Lagrangian tomograph of the first Lagrangian submanifold, and ds is a smooth measure on B. Then there exists a constant D depending on this tomograph and ds and metric on M prime, but not depending on L2, such that the integration of this function is defined by the number of intersection points of the image of L1 of under the Lagrangian tomograph and L2. And this integration is dominated by the constant d times the volume of the second Lagrangian submanifold. So now we are getting toward the Yomdin's theorem because Yomdin's theorem connects the topological entropy and volume, and this Croft-Jones inequality has the term volume. So we are now getting there. Okay, here is the sketch of the proof. So for each number sigma, positive number sigma, the number of bars in this persistence module of length greater than epsilon is finite, and hence only finitely many grading degrees contribute. So there exists a finite subset A sigma of the set of integers such that the number of bars here is just the sum of the number of bars from its contributing degrees. And choose a k-semi-admissible Hamiltonian function h satisfying the constant part of h is big enough. In this case, 1 plus 3R1 is good enough. Then, as we saw earlier, the relative symplectic cohomology is isomorphic to the Floer cohomology of single Hamiltonian. And we also know that the lowercase of action function variant of action functional satisfies the following chain of inequalities. Especially the first inequality can make us estimate this number of bars using this huge chunk. That was our first step. So next step is to estimate this big chunk. So consider the diagonal delta of m times m and the graph of the Hamiltonian diffeomorphism phi h sigma, and I will denote this graph by gamma sigma. Since every element of the Floer complex of sigma h arises from an intersection point of the intersection of delta and the graph, this one is the number of bars in this Floer cohomology is less than or equal to the number of intersection point of delta and gamma sigma, and we can intersect this with k1 plus r1 times k1 plus r1, where k1 plus r1 is the union of k and the first third of the color, because only the lower orbits contribute. So now we have the estimation of this one. And now it's time for Lagrangian tomograph to play. So let's say delta S is a Lagrangian tomograph of the diagonal delta, and we may assume that the Hofer distance between this diagonal and its Lagrangian tomograph is small enough so that so here we can replace epsilon by 2 epsilon and delta by its Lagrangian tomograph delta S. So we have this kind of inequality. So the bars of length greater than 2 epsilon is less than or equal to the intersection, not the number of intersection point of delta S, the Lagrangian tomograph of delta, and the graph of the Hamiltonian diffeomorphism. And we denote this number by n sigma s to use Croft-Jones inequality. Then by Croft-Jones inequality, the integration of this function n sigma s is dominated by some constant times the volume of this one, right? So therefore, if we integrate both sides, we have the number of bars of length greater than 2 epsilon in this persistence module, is less than or equal to some constant number times the volume of the graph of Hamiltonian diffeomorphism phi h sigma intersection with the k1 plus r1 times k1 plus r1. Okay, now Yomdin's theorem. So 2 epsilon Barcode entropy of the relative symplectic cohomology is by definition this. And we have seen that from the chain of estimation, this number of bars is less than or equal to the volume of the graph intersected with these k1 plus r1 times k1 plus r1. And it is just the volume entropy. So we can apply Yomdin's theorem now. So volume entropy is always less than or equal to the topological entropy. So this is always less than or equal to the topological entropy of the Hamiltonian diffeomorphism of H restricted to K1 plus R1. And from the basic properties of topological entropy, this topological entropy can be computed as the slope of H times the topological entropy of the reflow on the boundary. And taking epsilon to 0, the Barcode entropy of the relative symplectic cohomology is less than or equal to the slope of H times the topological entropy of the reflow. And we can do something more because this slope of H can be anything as long as it satisfies this. The constant part is greater than or equal to 1 plus 3r1. So let C prime be the infimum of such SH such that the constant part of H is greater than or equal to 1 plus 3r1. Then we have a refined inequality. So the Barcode entropy is less than or equal to the constant C prime times the topological entropy. But in general, this number C prime depends on the choice of R1, the length of the color. So we therefore denote it by C prime R1. So to further constrain this number, we consider the maximal color length. So let R max be the maximal color length of boundary of K such that K union boundary of K times 1 to 1 plus 3R max can be symplectically embedded into M. And we then define the constant C by the infimum of such C prime R, where R runs from 0 to the maximal color length. And hence, finally, we arrive at our main result, final destination. Thank you for your attention.
Thank you. Are there any questions? So can you say something about the let's say the Barcode entropy of the relative symplectic cohomology divided by the constant you have, right? Which depends on the embedding, like for different embeddings, and maybe compared to the absolute symplectic cohomology, like the.
Oh yeah, so you mean this constant C, right?
Right, right.
Yeah,
so it depends on. Right? So it depends on. This C depends on M, right? It depends on the embedding you have.
Yes, it depends on the embedding. So if in the case of absolute symplectic cohomology, this becomes one. So it recovers the known result by Fender, Lee, and so on.
So this relative symplectic cohomology divided by C is always smaller than the absolute one?
Usually C is greater than 1. But in the case of absolute symplectic cohomology, this becomes 1. Actually, we can compute it explicitly. So yeah.
I think that the question is whether can you get a better bound on the topological entropy by using relative or versus absolute.
Can I get a better bound? I'm not sure at the moment.
Okay, I think Felix have a question also. Yeah.
But do you have example where the left-hand side of the lower line is positive?
That's a good question, and I am still working on it. So hopefully I can find a lower bound, a non-trivial lower bound as given in other papers by Sinelli, Ginsberg, and Gurel, Mazzucchelli. Yeah. Hopefully I can get it. Someone can get it.
So you work in small dimension or in a specific geometry?
I don't know. I think I need some more knowledge about dynamical systems, like hyperbolic sets and everything.
Okay,
Thank you.
thank you.
So, excuse me, there were the conditions that you mentioned at some point about something like index bounded, correct? Could you remind me, could you remind us, because I sort of forgot this condition somehow.
When I use the condition or
No, but what was it?
what was it? Okay. Yeah, that's the definition. So if we fix a Conley-Gender index and we consider the set of every Reeb orbit of that corresponding Conley-Gender index,
Okay.
and we can consider their period, and that period, the set of period is bounded.
All right. Okay. Thank you very much.
Well,
So, if some part of of your proof follows kind of this method that Sinelli, Ginsburg, Gurel use, like so the Crofton formula and also this Lagrangian tomograph part, right? So they use this.
yes. Mhm.
Maybe I think the Crofton formula was used in this context. Where was it used first? Maybe Felix used it in some early paper of his with Marco or some. So this is just like about references related to your work.
Okay.
I'm just asking. So where did this appear first? Maybe.
Where did I mean, the first reference that I learned this Crofton's inequality was from Sinelli, Ginsburg, and Gurel.
Uh-huh.
No.
Right. Okay, but maybe Felix is here. Maybe he can say some additional word in case he has more. But he's not here anymore, I think.
We did that only in a special case of potential bonds.
Right. Yeah, yes. But
So
but still, I remember.
we use a global vibration. So the idea here is that you can localize the vibration.
I understand, but it did appear in your paper, right?
Yes. Well, the idea appeared by Magnier and Paternain in the geodesic setting.
That's right. Exactly. Yeah. Because I've been using some of this recently myself in some with Giovanni Ambrosioni and with Paul Biran, and so somehow it felt familiar in some level.
Okay.
But we also use it in a cotangent bundle, basically. Yeah. Right. Very good. Thanks.
Okay.
Okay, so let's thank them again.